Hi and welcome to this presentation of solutions, and also I will show the results at the end. I hope you enjoy the contest. We had a fun time preparing it, and I hope you enjoy the problems. Okay, so let's start. Okay, so the first problem, which was probably the easiest problem, I think, was the bus lines problem. In this problem, you were given a set of nodes labeled 1 to n. You were tasked with connecting a graph with m edges such that the sum of the endpoints are distinct. And by making a connector graph, I mean you have to connect everything. And there are many ways you can do this. My own favorite construction is probably this. So start by connecting node 1 with all other nodes. Okay, this will connect the graph, and it will also use up all the possible edges with the lowest possible sums. Right, because connecting it with 1 would make the smallest possible sum. And then to add more edges, what you do is you connect the node n with all other nodes, and this will make all the largest sums of edges. Yeah. And finally, just to note that this will actually use up all possible sums, because the smallest sum you can have is 3 by connecting 1 and 2, and the largest sum you can have is n plus n minus 1. Which you will get through this construction. So it's not possible to add more edges than this. Okay, that was that. And the second, I think, easiest problem was dexterity save. I noticed that people didn't really think maybe that it was the easiest when they looked through the problems, but I think it might have been. Okay, so in this problem, we were given the model of a dexterity saving throw in B and B. And the question was, how do you, what is the probability of succeeding this dexterity saving throw? Okay, and it's definitely not related to D&D in any way. Okay, so what's the key inside there? Well, if you look into it, you can see that there were actually not that many dice, and each die had not that many sides. So if you think about it, you notice that the number of possible outcomes are actually not that large. And because of this, we can just loop over all possible outcomes. Yes. And then some details also about the implementation. So because the number of dice we have, it can vary. So we have to code it in some kind of, we can't just do nested for loop straight up. So using some kind of recursion usually helps here. Yes, okay. Now for the third problem here, alto singing. So in this problem, you were given a song, some list of tones, and a vocal range. And the task was to try to somehow transpose, that means shift the song, so that you minimize the number of accidentals. Okay, and also after you've done this, you should also count how many such transpositions exist. Okay, and just as an example, what I mean, well, to the left here, you can see a song here, right? You can see D4, D4, E4. So these are the tones, and the 4 here is octave, and then we have this sharp here, which is accidental, and this notes a tone higher than F but smaller than G, basically. And our goal is to somehow transpose the song in order to remove this. And in this example here, if you transpose it up by 5 steps, you see that you will get something that does not have any accidentals at all. Okay, so now how do we do this? Well, the first thing to realize is that there are really just 12 different tones, right? So there are really just 12 different, fundamentally different kinds of transpositions. So really what we should do is just we should go through all of these 12 different transpositions and just see which one of them minimizes the accidentals, or if many of them minimize accidentals. That's also something interesting, right? And then we answered the first question: how many? What is the minimum number of accidentals we can get? And then the second thing we have to do is we have to count how many of such transpositions exist. And what we do then, number of accidentals is written. Yeah, I don't know. Okay, but what we do then is we one of the things that makes this kind of nice in order to count this is that, at least this is what I really like to do, is that you start by transposing the song down to the lowest possible note you can have, and once you've done that, it becomes actually somewhat easy to count how many octaves up you can go. Yes. Okay. So if anyone had any issues like implementing this, I would really suggest trying to transpose the song down before you start trying to transpose it up. Okay. And that's it for that one. Okay, so now for the costly contest. So this is a pretty long problem statement, but I will try to give a short version here. So in this problem, you were given m participants and m available problems. And you were given the task of designing a contest of duration t, and it should be split into k different age divisions. And what you wanted to try to do was you wanted to try to minimize the total number of prize winners. And prize winners, you win a prize if you solve the most problems in a division. Yeah, so this is what makes the contest costly. Basically, they give out prizes to everyone that like comes first or comes in tied first place. And in order to try to lower the cost, then they ask then, how can we make this contest so that so there's as few prize winners as possible. And then there's also some model about how quickly a participant solves a certain problem, right? So what we should do now is we should both make the divisions, we should pick up the problems for the divisions, and that's the task. Okay, so first thing to think about is what happens in the k equal to 1 case when we have a single division. Well, in that case, it's actually kind of easy to understand the one thing at least. The fastest participant will obviously win a prize, right? Because he will solve at least as many problems as anyone else. Second thing to realize is maybe a bit more difficult. So here's the idea. So think about the dead time, like the time the fastest participant spends at the end of the contest not doing anything, right? We really want to minimize that time, because if we minimize that time, then like it's harder for anyone else to try to even match his score. So that kind of becomes the optimization problem here. And now the question then is, how do you pick a problem set that minimizes this dead time? Well, So what do you, well, first you find the fastest participant, then you, so how do you do this pick? Well, what you do is you solve a subset sum problem for minimizing the fastest participant. And this will run in order m times t time. And and then we can simply count how many people could match it even with this optimal problem set or n time. Okay, and that was everything for k equal to 1. Now, for k greater than 1, you have to think a bit more about it. But it turns out we can actually just reuse the solution for k equal to 1. So why? Well, think about this example. Okay, so what I've done here is I've given so everyone that didn't win a prize in the end for the k equal to 1 case, I've written that as an L here. And everyone that won a prize, I've written as a W. Okay, so this is just some example here with 7 participants. Okay. So and here's the idea. Suppose we should make a okay, I spelled something wrong, but suppose we were should make 4 different divisions. Okay, for this example up here. What we could do then is we could just pick one winner into every division, and then any division we have left, we still have to make. Well, we can just pick a lone guy, and he can compete alone in that competition. And if you think about this, what this means, that you can do this kind of thing, it turns out that you can reuse the solution for k equal to 1 case. And what you really get is just that the general solution would just be the maximum of k and the solution for k equal to 1. Okay, that's problem C. Okay, and time complexity n. Well, order n for it's quick in n, and then m times t for in the subset sum problem. Okay, now we get to the even electricity. So yeah, so in this problem, we were given a series of data points over n days. On the ith day, we were given information that SI units of solar powered electricity was generated. And we were also given information about that WI units of water flowed into a reservoir. Okay, and the idea now with this problem here is that we are allowed to change, like we are allowed to, whenever we want, take water from the reservoir and make it into energy. And then the amount of energy you produce in a day, let's just call it EI. And what we want to try to do is we want to try to control this amount of water in the reservoir in order to minimize the maximum amount of energy we produce in any of the days minus the minimum amount of energy we produce in any of the days. So we want to like make it as even as possible. And also there are a couple more assumptions that you need to use up all the water, and also there's an assumption that you can't have more than R water in the reservoir at a time. Okay, but yeah, so let's now think about how can we solve this? Well, one insight is that we could make a function which, let's just call it check LR. And that function, what it does, it checks if is it possible that we keep the energy production for every day between L and R. We can actually make such a function run in order and time. So this is exactly solving the problem, but it's almost solving the problem. And how we do this is that what we do is like we simulate it from day 1 up to day n, and then we keep track of how much water can we have at the reservoir at the end of day I, right? And if you think about it, what it will actually be, it will be an interval. So we could end day I with an interval of water, like at least at most this much, and the least amount is this much. Okay. Okay, so that's so you can basically do this check LR, right? But that's not solving the problem straight up. And then we need another insight. And the way I think of it is that if you just look into this like check, what does it actually do? What you realize is that it actually tests the L and R bound separately. So we are kind of a little bit of abuse of notation here. What you can think of it is just, you can think of when you do a check LR, what you can really do is just check L and infinity and check minus infinity and R. That's just how I'm gonna note it. But yeah, so you can basically split up this check function. And that has huge implications. Because now we have it split up, then finding the best lower bound, well, then we just have to binary search on this check L function. And to find the best upper bound, we just have to binary search on the check R function. And yeah, so it just becomes a binary search problem. And then, yeah, and then about the end. So our check function took order and time, and then we have to do a binary search over all possible L and R values, basically. So something like 10 to the power 9 here. So that's why I've written n log m. Okay. Now for the next problem. So a forgotten homework problem. So in this problem, you were given a matrix, an n by n matrix. You were given 2 indices, and you were given an incomplete sequence. So a to the power 1 of ij, so index ij in the matrix, a squared, so that's a squared matrix, ia index, and so on, all the way up to a 2n minus 1 ij. And using all of this, you should output the answer. Yeah, you should try to find the unknown number in the sequence, the last thing. So yeah, so just a thing. So this isn't something I've written here, but I just wanted to mention it. So you can, of course, try to multiply the matrix and keep like trying to do that. And there are different approaches. There is one version which is order n cube, and there are like different. But the problem is that the matrix is just so huge that this is too slow. So we have to come up with something smarter. Okay. So now for the quick solution here. Okay, so first let's just, for notation wise, have ak equal to, yeah, small a, yeah. And then what's the key insight here? Well, the key insight is that this sequence actually has a very specific pattern. So what do I mean by linear recurrence? If you haven't heard about this before, so just a good example of this is the Fibonacci sequence. And in the Fibonacci sequence, what happens is that if you know like if you know the two previous numbers, you can calculate the next one. So what I'm saying here is basically that if you know the previous n numbers of this AK sequence, then you can calculate the next one. And then we have two questions. Well, why? Like why? Well, there is a theorem that says that this kind of sequence exists. So let me just go into this a bit. So the theorem basically says that an is equal to this. You can see here this sequence of some constant times an minus 1, some other constant times an minus 2, and so on, all the way down to the identity matrix. So that's basically what Cayley-Hamilton theorem says. And now we wonder why does this mean that we have a linear recurrence? Well, a couple of things. One thing we can notice, you can multiply both left and right hand side here with a or two a's, or I don't know how many a's you want. And this means that we actually have a formula here for any power ak where k is larger or equal to n. Second thing is that we can, like, since this is just an equality of matrices, we could just take indices everywhere and just look at one element, right? So let's just focus on this element ij. Then we see that we have this kind of formula, and this is exactly, having a formula like this is exactly the meaning of having a linear recurrence of length n. Okay, so we know that such a linear recurrence exists. Now the question is, how do we find it? Well, there is an algorithm for that called Bergkamp-Massey. Okay, so what does it do? Well, it finds the shortest linear recurrence given a sequence, but it needs twice the length of the shortest linear recurrence. Like, it needs to know the sequence up to a certain length in order to do it. And now that's the last technicality of this problem, which is probably the thing that people was surprised about. So the linear recurrence in this for the matrix here can be for the sequence, can be n long, but we were only given, so we need 2n values, but we were only given 2n minus 1 values in the input. So we somehow have to find one more value. So how do we do that? Well, let's look back at Cayley-Hamilton theorem. And let's focus here on I want to focus here on you see the thing to right here, I and ij. That tells us that the zero, like if we were to like come up with a zero value in the sequence, it should be that ij basically. So the choice you have to make for the a0 is 1 if it's on the diagonal, or 0 otherwise. Okay. Yes, and now we basically have the solution here. So conclusion is, start by making a0 equal to, 1 if I is equal to j or 0 otherwise. Run Bergkamp-Massey on the sequence. These are 2n values, so this will work. It would take order n squared time. And then we have the linear recurrence, and then we can just calculate a to n. So we never ever used the matrix. It was only there to make people think maybe we could multiply it, but no. Okay. So that's the solution for that problem. Okay, so now let's do the last problem here. Forgotten homework. So in this problem, there were n numbers laid out on a circle. The same number can occur multiple times. And what happened here is that alpha and beta are playing a game. Okay, and the idea is that alpha thinks of some number x. He doesn't tell it to beta. But beta tries to guess it. And what can beta do then? Well, beta can pick some y on the circle and ask alpha, which direction? Oh, sorry. That was a mistake. I put the wrong author, sorry. And ask which direction does this y lie? Like if you want to go from y to x, which direction should you go? Clockwise or counterclockwise around the circle? And the thing is that if there are multiple y's and multiple x's, then alpha, or even if they are on completely opposite side of the circle, then alpha can just answer whatever he wants. He can just pick. So he basically doesn't tell you anything if such an occurrence happens. So so for some y and x's, it will be an interesting question. For other y and x's, he can just say whatever he wants. So what's the task now? Well, the question is, for which x is it possible for beta to guess the x, given that beta can ask as many questions as it wants. Okay, so I will now show two different solutions here. So one is a cubic solution, and this, we intended this to not work, but heuristics and so on, you can't possibly speed this up. And that's also why n was so extremely large in this problem here. That was to try to kill off these cubic solutions. But let's just give the easiest one, the basic one. So what you can do in order n squared time, you can calculate this matrix here, matrix of xy. And you make it 1 if alpha needs to answer clockwise on the query xy, or 0 otherwise. And that's if it is forced to. That's the point. And you can do this kind of calculation. Okay, so let's now think about the question of, can we distinguish two different x's? Because if we can distinguish different x's, then we can like use that and we can try to figure out which x alpha is thinking of. But if we can't distinguish two different x's, then it's impossible to figure out if it was x1 or x2 that alpha was thinking of, right? So let's try to think about that test. And it turns out that the test you really want to do then is you want to see, does there exist, like to be able to distinguish your x's, what you need to do is you have to think about, does there exist a y such that alpha answer clockwise, is forced to answer clockwise on one and counterclockwise on the other, or he's forced to answer counterclockwise or clockwise. And that's what these matrix things here are. And so you can just do this for all x1 and x2. You can just go over all of them and try to see if there exists such a y, and this will run in order n cube time. Another thing you can think about is that these matrices here, they are really just bit checks. So you can just store everything in some kind of bit set, and then you can try to optimize these kind of calculations using bit set. And that will give you a bit faster solution, but both are too slow because n is so incredibly large here. Okay, so now the interesting question, how do we do the quadratic solution? Well, so for the quadratic solution, we can't just think about matrix, we have to think about the problem a bit. So here I've just drawn a bit of an example here. So let's say some number x occurs 3 times on the circle. Then if you think about it, there are two like really interesting intervals here. One interval which I would call here clockwise, and one interval I would call counterclockwise. And the idea is basically that if some y exists here, then it has to, like if you ask the query xy, it has to point up to say clockwise. And same thing here, if you ask for some y that only exists here, it has to answer counterclockwise. And if a y exists somewhere outside here, then alpha can answer whatever it wants and you will not get any information from it. So there are these two really interesting intervals for every x, and you find them by like cutting through the center of the circle. Okay, so what exactly is the test then? When for which y will alpha be forced to answer clockwise? And the test then is all of the y's on the circle must lie inside this interval. Only if that happens will alpha be forced to answer clockwise. Or likewise, only if all the y's lies inside this counterclockwise, only then will he answer, if and only if, then will he answer counterclockwise and be forced to answer it. Okay, so we have these intervals here. So okay, so let's go on and think about, so you remember the x1, x2 I was talking about before. Let's try to think about it now in terms of these intervals. So I tried to draw a figure here. So I have the old figure here before. So there is this interval here, which is the interval where you were forced to answer clockwise if you ask the query x1, y. And then under here, you have another thing. You have an interval now for some x2 I've drawn. And inside of this interval, you're forced to answer counterclockwise for x2. Okay. And our goal is to try to distinguish x1 and x2, right? And if you think about it, what it means for a y to be able to distinguish them, it means that all occurrences of that y must lie inside their intersection. So only if it lies inside of this intersection here will alpha be forced for x1 to answer clockwise and for x2 to be answered counterclockwise. Okay, so now we have a really kind of weird question. So for each pair of x1 and x2, then we look at this intersection here, and we ask the question: does there exist some y that only exists inside that query, inside of that interval? Right. So that's what we've broken it down to. That's basically just the question. Given an interval, does there exist a y occurring only inside that interval? And it's actually not that hard to compute this, because what you can do is you can think of this is kind of like a monotone property. Basically, once you make an interval large enough, then this will happen, and all larger intervals will have this property. So for each like starting point of the interval, you can keep like for a starting point of the interval, you can try to keep track of where does it end. Where's the first point where we contain all, like, there's some y that lies, all occurrences lies inside the interval. So we can, basic thing is then, if we can do this kind of thing, we can both pre-calculate everything in order n squared, and we can store it in just order n memory even. So we can actually solve this kind of problem really easy with some pre-calculation. Okay, and yes, so some conclusion here. So the time complexity solution will be order n squared, and the memory complexity will be order n. Okay. Yeah, and sorry for the author, like the error in the author there. Okay, so yeah, now I'm done with the presentations, and I will now go on to show the, let's see, I will now go on to try to show the, let me switch here, the results. Okay, so we can see here what's happening here. So, so it's actually kind of like an interesting thing here. So David currently has a possibility of both winning and coming third, because there are two other people that possibly could win, Joachim and Morten. Okay, so this is like a tied place here, pretty interesting. Let's go on here. Well, Fredrik could still take another problem, and that will actually also put him pretty high up on the list, or maybe not. Yeah, I don't know, but yeah, there's some interesting here, and yeah, fun to see so many people doing the contest. Yes, okay. So Per, could you unfreeze it? So let's see here if it's unfrozen. Yes, okay. So now we see what happens. So they were actually able to solve G at the end, and he got all problems. So yeah, he's the winner of the KTH challenge for this year. Great work, great work. And yes, unfortunately, the other two solutions didn't pass. Yeah. And also nice there, Fredrik also got, I think, problem E there in the end also. Okay, but I think that's it. Okay, so thanks for us for this year. Yes, it's been fun. Hope you come back for next year.